So this video is the last one on using on the central limit theorem in chapter 7, and it's on using the central limit theorem. So it's important to understand when we can use the central limit theorem. If we're being asked to find the probability of the mean, we use the central limit theorem for the mean. And remember, that has one specific, new mean, it's the same, and standard deviation. And if you're being asked to find the probability of a sum or a total, we use the central limit theorem for sums, which has its own new mean and new standard deviation. So this also is for percentiles, for means and sums. But it's important to know that if you're being asked to find the probability of an individual variable from your original distribution, we're not going to use the central limit theorem. We're going to use the distribution of that random variable. So we spent time looking at the binomial distribution, the uniform distribution, the exponential distribution, and the normal distribution. So just be careful when you're looking at a problem and make sure you read it carefully. And if it's asking about an individual, you use that distribution, the original one. But if it's talking about a sample mean or a sample sum, then you can use the normal distribution because of the central limit theorem. So try it 7.8. A study involving stress is conducted among the students on a college campus. The stress scores follow a uniform distribution with the lowest stress score equal to 1 and the highest equal to 5. So we know from uniform distributions that the mu of the original distribution is the lowest plus the highest divided by 2, or 3. And the standard deviation is the square root of the highest minus the lowest square divided by 12, or in this case, 1.15. So that's a uniform distribution. If we're being asked about an individual, we would use that. Using a sample of 55 students, though, find the probability that the mean is less than 7. So we're being asked about means. Central limit theorem, ding, ding, ding. We use the normal distribution. So what's the probability that the sample mean is less than 7? And then we're going to find the 80th percentile for the mean of 55 scores. So this problem is out of the book, and I kind of thought we'll do it, right? So if we go in here and we find the probability, we can use the normal distribution. We're looking for the value 7. The mean we saw was 3. Our standard deviation, again, you can put the formula in. I'm just going to type in the 1.15 and use the word true. We get 0.997, almost 100%, or one probability of 1 that the sample mean is less than 7. And so the reason I was sort of hesitating is that the scores only go up to 5. So what's the probability the mean is less than 7? Like, probably pretty good. Did anybody catch the mistake I made? I used the original standard deviation in that formula. We're going to find out that it's pretty, okay, so I apologize for that error. So our new mean is the same. So mu sub x bar is 3, and sigma sub x bar is 1.15, the old standard deviation divided by the square root of the sample size. I'm rushing and I made a mistake. So it is going to change our probability, but you'll notice it doesn't change it statistically in a huge factor. All right, so now I have the right standard deviation, 1.15 divided by the square root of 55. So see, it was close to 1 before. It is exactly 1 now. So those scores, like I was saying, are less than, they're 1 through 5. So the mean is 100% chance it's going to be less than 7. Anyway, here it is using the 0.1551 that you get if you type this in. So I'm sorry about that. So let's find the 80th percentile for the mean of 55 scores. So remember, with percentiles, we're going to use the norm.inv formula. So what's the probability? We're looking for the 80th percentile, so 0.8. Our mean was 3. Our standard deviation, 1.15, divided by the square root of our sample size, which is 55. And that's it for this formula. And we get 3.13. So try it 7.8 continued. So we have that study involving stress conducted among students on a college campus. We have a uniform distribution, lowest score equal to 1 and the highest equal to 5. Our original distribution has a mean mu of 3 and a sigma of 1.15. We have a sample of 55 students. We're going to find the probability that the sum of the stress scores is greater than 170 and the 85th percentile for the sum of 55 scores. So if we go over to Excel, we are going to use that information that we've already seen. So originally we were looking at the mean, and now we're looking at sums. So we have to remember that the new mean, the mean of the sum of x, and the standard deviation of the sum of x is different or are different. So because we're looking at sample sums, our new mean is going to be our sample size times the original mean. So 55 times 3. And our new standard deviation of our sample sums is the square root of our sample size. So the square root of 55 times the original standard deviation of 1.15, which is about 8.53. So 165, 8.53. So in here, greater than, so we're going to have equals to 1 minus our normal distribution. So our x here is 170. We want to know the probability that the sum of the scores is greater than 170. The mean we saw is 55 times 3 or 165. The standard deviation, I'm going to type square root times 1.15. So SQRT of 55 times 1.15. You could just put in that number. But again, we have rounding errors a couple of times here. So, and then the word true. So about 0.2789, the probability that the sample sums are greater than 170 is 0.2789, or a little more than 27%. Find the 85th percentile for the sum of 55 scores. So again, norm inverse. Our percentile here is our probability, so 0.85. Our mean was 165. Let me just double check that. Yep. And then our standard deviation is the square root of 55 times 1.15. So 85% of the sum of the sums of samples of size 55 are greater than, are less than, or equal to 173.8. That's the sum of those scores. Suppose, this is try at 7.9 from the book. Suppose a market research analyst for a cell phone company conducts a study of their customers who exceed the time allowance included on their basic cell phone contract. The analyst finds that for those people who exceed the time included in their basic contract, the excess time used follows an exponential distribution with a mean of 22 minutes. And we know for exponential distributions that when the mean is 22, it's the same as the standard deviation of 22. So using a sample of 144 customers, we're going to find the probability that the mean time exceeded is between 20 and 30 minutes. And we're going to find the 75th percentile for the mean of 144 excess times. So central limit theorem, we don't care that it came from the exponential distribution, though that does help us know something about the mean and the standard deviation. Because we're looking at sample means, we can use the normal distribution. This is a between problem. So the first thing we have to think about is our new mean. For means, it's the same as the original mean. And our new standard deviation is the original standard deviation divided by the square root of our sample size. Now, 144 is a perfect square. So this is the square root of 144 is 12. So you could do 22 over 12 or 11 over 6. And it's 1.83, I believe, repeating. So you could put it into Excel, or you can use the number. We've talked about that a couple of times. But these between problems, so the normal distribution, I'm going to use the bigger number first this time, 30. Our mean here is 22. Our standard deviation is 22 divided by the square root of 144. And I'm going to use the word true. And I'm going to subtract off the normal distribution for the smaller number, 20 minutes. Same standard mean, and then standard deviation. And the word true. And we get 0.8623. So the probability that the mean time exceeded is between 20 and 30 minutes is 0.8623 or 86%. The 75th percentile for the mean of 144 excess times, we're going to use the norm inverse. 75th percentile as a probability, 0.75. 22 is our mean. 22 divided by the square root of 144 is our standard deviation, and we get 23.24. And for this problem, that means that 75% of the mean excess times is less than or are less than or equal to 23.24. So same problem, but now we're going to talk about sums. So this is mean excess time. What's the probability that the sum of mean excess times is at least 3,000? So that's greater than or equal to 3,000. And the 85th percentile for the sum of 144 excess times. So again, remember that the point of this video in this section 7.3 is to think about the difference between mean and sums and use the different standard deviation and means for those things. So this is a sum problem. So our new mean for our sample sums is the sample size, 144, times the original mean of 22, which gives us 3,168. And our new standard deviation of the sample sums is the square root of 144 times 22. Again, this is just 12, so 12 times 22 is 264. Our greater than problems are always 1 minus, and it's central limit theorem says we can use the normal distribution. So 3,000, that comes from our problem. Our mean here, 3,168. I'm not putting a comma in there. I don't know if we brought that up before, but that would confuse Excel. So no commas when you're writing the numbers. The standard deviation is the square root of 144, 12 times 22, the original standard deviation, and the word true. So the probability that our sample sum is greater than or equal to or is at least 3,000 is 73.77%. Or 0.7377. 85th percentile problem, we're going to use the norm.inv. So 0.85, the mean here, 3,168, and the standard deviation, 12 times 22. Again, if you want, you could set it up so you have the mean and the standard deviation in cells right there, and you can just click on those cell references. So 3,441.6. So 85% of our sums will be less than or equal to 3,441.6 minutes. Try at 7.10. Based on data from the National Health Survey, women between the ages of 18 and 24 have an average systolic blood pressure in milligrams of hemoglobin of 114.8 with a standard deviation of 13.1. Systolic blood pressure for women between the ages of 18 to 24 follow a normal distribution. So we know that this one comes from the normal, that has a normal distribution, the original random variable. And so if one woman from this population is randomly selected, find the probability that her systolic blood pressure is greater than 120. So this is that individual that we're being asked about. So we're going to use the original distribution. In this case, it does a normal distribution, but we're not going to change our mean and our standard deviation this time because we're just talking about one person from this study. And I said, so this is asking about an individual. So probability that one woman has a systolic blood pressure greater than 120, 1 minus the normal distribution of that 120, our original mean, our original standard deviation, and the word true. So it's maybe a little confusing because we've been using the normal distribution all along, but please notice that when you're being asked about an individual, you're going to use the original mean and the original standard deviation. You're not going to change them at all like you did for sample means and sample sums. Same thing, but if 40 women from this population are randomly selected, find the probability that their mean systolic blood pressure is greater than 120. So now we're talking about a sample and we're talking about a mean. So it's the sample means. So we're going to use the sample mean central limit theorem protocol. Okay. So it's a sample mean. So that means we have a new sample mean, which is really the same as the original one, but our standard deviation has changed here. So now the standard deviation of this should say X bar is the original standard deviation of 13.1 divided by the square root of 40, which is about 2.07. So greater than problems, 1 minus the normal distribution, 120. There's our sample mean, our sample mean standard deviation, and the word true. And there's only about, so 0.006 is about a 0.6% chance that the mean of the 40 women, the mean of the sample, is greater than 120. So it's very different than just one individual from the original distribution. If we took a sample where 4 women, if we took a sample of 4 women between the ages of 18 to 24 and we did not know the original distribution, could the central limit theorem be used? In theory, if we don't know the original distribution, a sample of 4 is too small. We like to have larger samples. Now, we were told that this follows a normal distribution so that we could just use the normal distribution. That would be all right. But technically, the sample size is too small in this case for the central limit theorem. So that's the end of the video for 7.3, just looking briefly at the differences between the central limit for means, the central limit for sums, and then an individual from the original distribution and what you do when you're asked about that.